So I will actually start by talking about vegetation patterns and particularly about, about climate, vegetation, soil and water interactions in drylands. These areas are obviously characterized by one important point. The important point is the fact that the limiting resource for vegetation in these areas is obviously water. There are other limiting resources, like obviously nutrients, but these in these areas are typically carried by water itself. So to a first degree of approximation, you can sort of consider them, if you do a very simple mathematical modeling, you can consider water to be the relevant resource. This obviously, what you see here is well, it's a picture for one particular dry area. It's actually the Negev desert in Israel. And what often is found in some of these areas, in arid and semi-arid areas, and it's actually more common than what you would think, and you can actually find some good examples even by going to Google Maps and looking yourselves, is actually vegetation patterns. And vegetation patterns, I have here a few examples. Vegetation patterns are can be found in several dry areas all over the world. As I said, you could actually yourself take Google Maps and zoom on certain areas in Niger, for example, and you will, with the resolution we have today, even be able to recognize some of these patterns. They range from having individual spots. This example is obviously just sort of, it's not a regular organization of spots. That's basically grass. It's a picture of grass we took in a dry area. But look, for example, at the same type of grass. Actually, no, it's a different type of grass, but the lawn which you see in the upper figure. So that, for example, is actually a lawn in a residential area, but still in the Negev. It was in a town in Negev, which was not appropriately irrigated for some time. And actually, while we were working on this formation of these patterns, we found, Moshe Shachar, actually, he found this example and took some pictures of this lawn. And that is actually quite striking example. That's a typical pattern I'm talking about. You recognize it immediately as a pattern because you see that there is a typical wavelength in this type of, there's a typical wavelength which characterizes a pattern. And so we have different, and the typical patterns you find go from spots, bands, another example of spots you can clearly see in this Google Earth image you see at the top right, to actually the opposite of spots, which is gaps in a dense vegetation. In the lower corner you see one example. And the other thing to be said about this is that they actually occur on a wide range of scales. We go from a few centimeters, which are the examples on the left, and that depends obviously also on the type, on the species which is involved. We go from a few centimeters on the left to several tens of meters, which are more typical for shrub-like vegetation. And I have another example to show you, which is this one. These are so-called fairy circles. Fairy circles are observed in Namibia, but they're also observed in Australia. So it's not Namibia in Australia, but it's Namibia, Australia, sorry about that. Fairy circles are interesting because they basically consist in low vegetation, basically grassland, punctuated by completely bare areas. And that's a good example of these gaps pattern which you saw before. Actually, there has been quite some debate in the literature in recent years about the mechanisms originating these patterns, these specific patterns. There are also other mechanisms which have been evoked, for example, the action of termites. But a lot of evidence is pointing to the fact that this is also an example, actually, of basically self-organization of vegetation in response to a limited resource, to water being limited. And Yet another example, and this will be my last one, is the classical one, which actually started a lot of work on this topic. Basically, I would say 20 years ago, which is about, which are these, what is called tiger bush. This is bands of vegetation, which strikingly organizes itself really in organized bands, which tend actually to be aligned along the isolines along a slope. So basically, they all vegetation is staying at the same altitude. So the slope is actually going across this pattern, across these bands of vegetation. And here we can start to see actually how these patterns are actually formed. These patterns are formed due to local feedback mechanisms, which act both at a very local scale where the vegetation is, and also at some distance from the vegetation itself. And the reason for that, and that is quite clearly illustrated by these tiger bush. This is the lower image is actually from one of the original papers which were describing this, and it shows areas of the world where such patterns have actually been observed. So you can see that it's actually a quite widespread phenomenon. So I think that actually this tiger bush is illustrating very well the mechanism. And it's basically, well, you see it illustrated in the top, again, above from one of the earliest papers. You see it in the top slide, where you can see that actually you have a band of vegetation, of low vegetation. Well, those are trees, but typically these are low trees slash, basically it's shrubs. And so you have a vegetated band and you have a bare area in between. And this bare area is basically acting as a reservoir to feed the band itself. You have scarce precipitation occurring in these areas. And also another element, which I will illustrate also in the next slide, is the fact that actually in these areas, typically infiltration in bare ground can be reduced significantly, or certainly infiltration is higher in areas where you have vegetation. For various reasons, vegetation is actually facilitating infiltration underneath the vegetation itself, both for the fact that actually vegetation is helping to accumulate dust and terrain around it, so basically forming a little mound, but also due to the fact that actually under vegetation you have an entire ecosystem of other species, also animals living, which are changing the soil and the ground, so burrowing also the ground. And so for these reasons, actually, it's quite easy for water to infiltrate under vegetation, whereas in the bare areas, you can easily have the formation either of physical or biogenic crusts. So basically, infiltration being heavily reduced. In particular, in drylands, you have cyanobacteria which act, which can form quite impermeable mats of organic material which prevent water from infiltrating. So there you can see how this could work, is that basically you get water falling obviously sort of uniformly everywhere, but on the bare areas actually water will fall but will stay as runoff on the surface. And at that point it will actually, since we are on the slope, it will be accumulating and feeding the vegetation band. So you see that water is not enough. We're in an area where water wouldn't be enough to sustain a dense cover of shrubs, but now since the shrubs organize themselves this way, they have a reservoir of water to feed on, and they're getting water from this reservoir. And the other point is obviously that the idea is that since they are getting water from the top of the hill, the water is flowing down, and then water is infiltrating in the band, you will have an area of active growth of vegetation, which is actually uphill, and an area of decay, which is downhill, where water will start to be scarce again. And so actually, and this is to some extent being observed, but certainly models it's well reproduced, these bands should be moving slowly uphill. So but this is a good example of such, and so basically I talked about feedbacks. Well, here you have a feedback in the sense that the two bands cannot be too close, because then this gap would be too narrow to give water to each of these bands. So that is basically, if you think of two individual bands, this picture obviously is periodic, so you have to imagine it to continue on the right on the top left. If you imagine two bands which are at a certain distance, they cannot be too close because they would be competing. So that's an example of competition at a certain distance for the same resource. The same way, actually, also, obviously, vegetation is facilitating infiltration locally, and so that is a positive feedback by which, when you have more vegetation, you will get more water, and so possibly facilitate the growth of the vegetation. So I made the example of the Cyanobacteria. Well, this is a quite striking, actually, image, satellite image of the Sinai and of Israel. What you can see in this image, actually, which is quite fun, is the fact that actually you can recognize a political border between the Sinai and Israel. And since this is a satellite picture, this is quite unusual. And it goes so far that if you zoom on a certain area, well, what is on the left is the Egyptian. This is actually the border, and that is the road is a patrol road they use to patrol the border. And the area on the left is the Sinai, is Egypt, and the area on the right is Israel. And the point is that the area on the right is basically all military zone, and it's so it's basically not very much used for human activities. The military do some stuff there, but obviously, this means that the vegetation is quite undisturbed on that side, or more undisturbed compared to the Egyptian side, where actually Bedouins can actually freely have cattle grazing also closer to the border. And this obviously heavily can disturb the vegetation crust. Not all the color you see is obviously vegetation crust, but vegetation crusts, biogenic vegetation crusts appear dark, and so it's part of the picture. So feedbacks, and so to summarize, we have a few feedbacks at work in these type of systems. So on one hand, we have we can make different examples of feedback. So the one you have seen now is actually an infiltration feedback. You have a local facilitation due to the fact that vegetation is facilitating infiltration locally, which certainly helps the growth of biomass, so that would be a positive feedback. And then you have a competition at a certain distance between these different patches. There are other examples of long-range competition we could introduce in this system. For example, well, one can think of is the fact that plants will also interact under the surface through their root system, and obviously larger plants, more developed plants with a more developed root system will be able to draw water more efficiently and may do so at the expense of new seedlings which are trying to grow. And so that's an example of a longer range competition also. And obviously, if you go on the slope, this type of feedback is exactly what I illustrated before for the vegetation bands. So with these ideas in mind, there was quite some activity, I would say 15, 20 years ago, to develop several mathematical models to explain these patterns. Also because these patterns are obviously so clean, and also they immediately trigger the memories from other fields of physics where you see pattern formation, and you think, well, this is something I can understand. In other fields of physics, I've seen such patterns, and they could be understood as some form of instability, of finite wave number instability. And so this triggered, obviously, the idea that the same similar mechanisms could be at work also in this field. So this led to a series of modeling work, which was, basically, many of these models, apart from some these models differ mainly in the amount of components of dynamical variables they include, basically, or the level of detail of mechanisms they are trying to include. Basically, you need at least two dynamical variables. In one case, you could use only one, but then you need to introduce some long-range feedbacks by introducing some integral terms to compensate for that. But, and basically, all of them, they rely on this instability mechanism, which is known, as I said, in other fields of physics, as basically a Turing-like type of instability. So the main idea being that in many cases, when you try to model these with differential equations, so partial differential equations, you would have two species. Typically, one species which two dynamical variables. You would have two dynamical variables, one typically working like an activator and one working like an inhibitor. So one activating the production of itself also. And then there would be a difference between these two because they would have different diffusion rates. And the combination of these factors is well known to be able to lead to a finite wave number instability. And we can see an example on that by illustrating one model. So this model, well, obviously, I'm illustrating one I participated in to develop. And so this model basically, well, it's just a one. It's not, well, as I said, there have been several papers and several approaches, but they're quite similar. This specific one has actually three dynamical variables because it distinguishes the water flow both on the surface and under the ground. So you have a soil water variable, which is the W you see at the bottom. You have an overland flow variable, so that is H, that would be the water standing above the ground. And then finally, you have a variable expressing the biomass density of your vegetation. So you have only these three elements. And you combine them in a PDE because those dispersion terms will be diffusion terms. And so basically, what you have is a system of three partial differential equations. And obviously, you introduce indeed the connection between these is introducing various terms to represent various physical processes at work. And particularly, you introduce the way how these interact. And so, say, the growth of the biomass will be a function of soil water. The infiltration, you can make it to reproduce these feedbacks. You can make it a function of the presence of biomass itself. Evaporation and root, what here is called root uptake, so basically transpiration, also will be a function of the biomass itself, etc. So if we translate this finally to a set of equations, well, this is nothing special. I mean, it's just one of the many possible models you could write, but basically this one had we used quite a lot as a tool because it allows to explore various different feedback mechanisms in it, because actually it has the potential to represent both these, basically all the feedback mechanisms I already listed. But in particular, it also is able to represent the root uptake feedback. The root uptake feedback requires you to have an individual plant to be capable of drawing water from its surrounding. And basically, we managed to do that by adding an integral term in the equation. So basically, you see that the equation for the biomass is a very simple logistic form, basically, plus a dispersion term. Dispersion itself and diffusion of the plant is represented by a simple diffusion. And the growth term is represented by an integral. So basically, it's an integral with a Gaussian kernel, which is representing the root system, which is drawing water from the surroundings. There's a technicality here, because it looks like a convolution, but it's actually not entirely a convolution, because the Gaussian kernel, which you can see here, actually is itself then a function of biomass. Basically, you want this width of the root system to be a function of the biomass itself. You want larger plants to have larger root system, etc. And this is a technicality, but actually interesting from a computational point of view also, that if you want then to simulate this, that obviously is inefficient. You cannot solve it by going simply to Fourier space. And actually, we managed in a separate paper, which I'm not citing here, to solve that by approximating this as a sum of convolutions. That's actually quite interesting technicality. Anyway, in this system, you have basically all the elements to start studying all the different feedbacks at work in this system. So to proceed, this type of equations actually, as I told you, well, if we just look at the stationary solutions and the stationary and uniform solutions, well, we discover that, well, you have a phase diagram like this, which is a function of precipitation, and obviously you have a bare state, which becomes unstable at a certain point, and you have a fully vegetated state above it. But actually then, when you now go and study the possibility for spatially varying perturbations, you discover that actually the fully vegetated uniform state is unstable to non-uniform perturbations. And so there is a finite wavelength instability in the system. And this actually leads to the formation of vegetation patterns. And actually, this is basically what you will find in many books about pattern formation. It's a mechanism which is, it's not entirely exactly a Turing-like mechanism, because we have complicated the problem by introduction of these integral terms, which make analysis a bit more difficult. But basically, in the essence, it is due to the different diffusion rates of the various elements. And in particular, if I go back once more, it's obvious that the diffusion of soil water in the ground and diffusion, so basically diffusion above of overland flow will be the fastest, diffusion in the ground will be slower, and dispersion obviously of vegetation is particularly slow. Okay, so to move forward, you get the formation of such patterns. So basically this branch, this uniform vegetated branch, is unstable to small perturbations. So here, these are numerical examples where we did simply a small random perturbation of these branches, and you see the formation of the usual sequence of patterns. So this basically almost, well, actually canonical series of patterns from spots to bands to gaps. And if you compare with a problem like Rayleigh-Bénard convection, you will find the same. And yeah.
Point, I mean, the lower bifurcation, the PC, the fact that that is not the usual S-shaped back-to-back, how we know, has to do with the threshold effect.
Well, it has to do with a particular, the exact type of bifurcation you have there depends on the obviously on what you choose to put up there in the equation. So in this case, it's that if you approximate these integrals with, since we have this dependence here, and if you approximate those integrals in the uniform case, you end up with a dependence on 1 plus b squared. So actually, that is not a simple logistic, but it's higher, has a higher power. So, but the same you could get also in a simpler setup, exactly. So that is. Okay, so this is obviously, as I said, it's sort of a universal sequence of which we recognize also in other other fields. It has been observed, and so this is the sequence of patterns is obviously a function of precipitation, but the interesting thing is that obviously that when you look more carefully into it, you discover that there can be a coexistence of various patterns. So here I use actually a picture from, which is not from this model, but from an earlier model, but it gives you the idea that actually these patterns have wide coexistence ranges. So actually, if you find one of these solutions and you propagate it to the left or to the right by slowly changing the control parameter p, you will discover that the system will stay on that branch for a longer time, and actually before falling in the end onto the next branch. Here in this picture, maybe a bit unfortunately, these branches are connected, but actually, well, they probably shouldn't. Anyway, so basically this means that you have wide ranges where you have overlap between different solutions. In particular, you have a range of stability both of this spotted pattern with the bare solution, which is by itself already interesting, So basically, the fact that you get vegetation patterning brings you to extends the range of existence of your vegetation. So this is really the main point, that vegetation this way is able to survive in a range where it wouldn't be possible other ways. But obviously, this is also interesting because this opens the possibility to study these problems like high hysteresis cycles. So originally, for example, the obvious thing you could possibly do is to interpret this by this coexistence of having both a bare state and a vegetated state as a possible simple mechanism for desertification. There are other things which you can do. You can, for example, play with transitions in these systems, which leads to some interesting considerations. For example, think of these two patterns, which are coexisting at the same precipitation level. So precipitation is the same between these two. And since we have both patterns which can coexist, we can have a transition from one to the other by possibly by perturbing the system. And what is interesting to see is that actually, if we look at something which will be of interest to other species in these dryland ecosystems, like, for example, we look at soil water profiles under the patterns, you discover that actually the one of the two patterns, actually in this case a spot pattern, is characterized by having actually a higher level of soil water underneath. So since you can actually go to the spot pattern also by reducing precipitation, and since this actually will still be true also at slightly lower values of precipitation, you have sort of the, well, if you want, the paradoxical conclusion that by reducing rainfall, you can actually get more water in certain places. Obviously, the total water will be less, but you can have actually more ecological niches for some species to live. So actually, that's quite, well, if you want, paradoxical conclusion. The other point is that, well, the other example is this one, where, well, this is just basically an example of how these transitions may happen. Here, simply, we took some bands and cut them, and you can see how actually the transition really occurs. And so really, you see, this is in a range where both the banded and the spotted pattern can coexist. And you see that just by introducing a small perturbation, so this could be an anthropogenic perturbation, the system prefers to go to the other state. Okay, so this example I showed in the earlier slide, that actually the vegetation is able to increase the amount of water underneath itself, is actually an example of so-called ecosystem engineering, which is typical for some of species in these areas. So this is something which ecologists have also discussed already before, that shrubs in desert areas may act as so-called ecosystem engineers. The most typical idea of an ecosystem engineer would be a beaver, of course, which modifies the environment to benefit itself, but in doing so, also this species is also benefiting other species by creating new opportunities, new niches where to live. And this is something which can be reproduced also with this type of, what we get actually also with this type of approach. You can see it more clearly here, where I take again the picture of before, but now showing also the soil water content underneath a patch, and you can see that actually this soil water content underneath a patch at a certain point for some values of precipitation actually can exceed this B branch, which is instead the branch which would characterize a bare area. So having the vegetation will increase the amount of vegetation, the amount of water you get actually under a patch. There are other curiosities you can go through quickly. One is, well, these are vegetation rings, which are sometimes observed in some of these areas. This is sometimes can be interpreted as being an example of the vegetation competing with itself at the center. So basically, this is a spot which grew too large, and so it is starting to compete with itself at the very center. I'm basically showing this because it's not because it's a very good approximation of this phenomenon, but it shows what happens when we initialize with a single spot in a range where actually the vegetation prefers to form bands. And you see, obviously, you would get something like this. Okay, so to move forward, actually, I show you, I wanted to show briefly this, which is an example where we used instead this approach to study actually competition between two species. And I think this is interesting because, well, you may know that it exists in ecology this principle of competitive exclusion, which is the fact that based on the number of resources you have, this would limit the number of species, which in the end you could possibly sustain, because actually you would always have one better competitor over the next in exploiting this resource. So that species would then drive to extinction the other species. As we discussed a lot in ecological literature, obviously this theoretical idea in practice is obviously superseded by a lot of exceptions. Basically, every time you introduce some variation to the theme of having perfect homogeneity, either in time or in space. What is interesting is that though here we are assuming that we have perfect homogeneity in space in the sense I never told you about any perturbation of topography, for example. So I'm always assuming that everything is perfectly homogeneous, at least as a mathematical problem from the beginning. And so we have two species. In this case, we take two species. One is pattern forming. So B1 would be pattern forming. The fact that B1 is pattern forming, you can recognize these are basically, these are simplifications of the equations you saw before. It's a simpler, more linear version of the equations you saw before. And the pattern forming species is recognized because infiltration is a function of B1 alone, not of B2. So B1 is a pattern forming species. It has a possibility to affect infiltration. It is controlling infiltration. B2 is instead another species which is not pattern forming, but it has a larger dispersive capability. So D2 is larger than 1. So it is faster in spreading. And just by having this combination, I do not have time to go into more detail in this, but just by having this combination, you get actually a quite interesting phase diagram exploring the coexistence of these two. So the first thing is obviously that you find a wide range of parameters. The two parameters here are the usual one, precipitation, as a control parameter. And the other one is C2. C2 is a competition parameter. It's controlling how much these two species are competing for water. You see it because it's controlling, it's in front of the W for the B2 equation up there. And so you get a quite complex picture, a picture which gets even more complex because there are different wavelength solutions possible for B1 which can occur. So that explains this detail which is zoomed there. So basically you see that little complex area down there, it's actually zoomed up there. And so you have a wide range where you can have coexistence of both of them. And obviously, since B1 is forming a pattern, even if B2 is not a pattern-forming species, it will form a pattern as a consequence because it's following the soil water given by B1. And more interestingly, also, you can have a transition to even oscillatory solutions in this, actually quite wide. It's a thin, but actually quite wide range in precipitation. It's a blue band you see over there. The other point which is interesting to notice is that, so basically here we see that just by joining these two, we are sort of going beyond the competitive exclusion principle. And the other thing which is interesting is that what you see on the left there is the range, is what you would have got by having only B1 alone. So the B1 species, which we let it go and analyze it by itself. And as before, we have a lowest point precipitation where the pattern can exist and the highest point of precipitation where it can exist is P low and P high. And P low and P high, again, here in the slide, they are basically that green band you can see there. That's a range where a pure pattern of B1 can exist. But now you can see that due to the coexistence, actually, there is a much wider range where they can actually coexist, which can go to much higher values of precipitation. Okay. Then we have another application or development, which is the fact that actually up to now I talked only about regular patterns. And regular patterns are quite striking, as I try to convince you, quite common. But obviously, more often than not, we find non-regular patterns in vegetation. And also, these non-regular patterns seem to have some structure to themselves, in the sense that there has been some literature discussing the fact that if you take some areas, that picture is terrible, should really find another one, that you take some aerial photographs of vegetation, you group the vegetation by size of vegetation patches. You can obviously make a plot like that, which is basically that's a probability of exceedance. So it's a cumulative distribution, not a PDF, but a cumulative distribution for these areas of these patches. And well, a physicist looking at that could possibly say, oh, look, it's a power law. Obviously, in log, a lot of things look like power laws, and so I would be a bit skeptical about this, but still, it is true that there is no clear peak. There is a broad range of patch sizes which are possible. And so let's put aside if that is truly a power law or not. The point is that indeed it doesn't look at all like the regular patterns we have seen so far. And this, at least for me, opens a mystery, because an interesting point, which is the fact that we really tried our best to write a model which has all the possible feedbacks and mechanisms for such dry land areas. We did not tune it particularly. We tuned it to be reasonable in the values, but you don't have to look for an entire PhD to find the values to get these patterns. Anything which is sort of reasonable from the literature will actually give you, under the right conditions, this type of behavior. So the question then becomes, okay, then the same model, if it's more or less a reasonable model for vegetation in dry lands, should also give you something like that. And at the first degree, it does not, and so that's the point. So, well, what we can get with a model like the one you saw before is obviously something like mixed states like these. So you can build up combinations like the one on the left-hand side in the ranges where, as a transients particularly, and in the ranges where you have coexistence of two types of patterns. But still, in that case, if you do a Fourier spectrum analysis, you would still recognize, but you recognize it also by eye, that there is still a dominant wavelength at work. So by analyzing more carefully what is the role of various feedback mechanisms in actually limiting the size of patches, it's obvious that if we want a broad distribution of patch sizes, we need to allow very large patches. And apparently, since the system prefers a finite wavelength, it's always trying to give me patches of only a given size. So by sort of screening the various feedback mechanisms and switching them on and off, you can sort of study how this is controlling the patch sizes. And basically, you find that most of them actually, they are limiting the patch size. So basically, what you would need in this case is to switch off the main mechanisms which are strongly limiting the size of the patches. So you need to avoid having something which is truly preventing such big guys, such big errors as you see there on the right from existing. So basically, the main point is that we can simplify the mechanisms at work, reducing them mainly to the infiltration feedback. And the infiltration feedback has also a typical length scale, which is given by you remember this H equation for overland flow, which is quite fast. But still, there's a typical length scale involved there because you have the diffusion rate, and then you have a time scale, which is the infiltration time scale. And by combining those, you can get the spatial scale, of course. And that spatial scale is what is really limiting the patch size. And so by going to cases where the diffusion rate is very, very high, so by going to a case where really you can get global connection between patches of all size all over the domain, you can actually, in the end, get a situation by which even such a model can give you solutions like this. So you get actually a range of scales being reproduced by this.
Austral is the name of a co-author, or it's the name of the...
No, Austral Wrapping is a phenomenon which is which occurs in solutions when where it's front dependent, so the curvature is playing a role. So small solutes will dissolve more rapidly. They have more atoms being exposed to being exposed, and so they will dissolve, and then they will deposit on flatter surfaces. So basically, the small guys are going away, and the larger guys are growing faster, and so that is facilitating the growth. And actually, I have a slide on that in 1 second, which is actually, well, I can go there directly, which is basically this. And so you can, so basically you can look at this phenomenon and you discover that actually, well, this is all a transient. The size of the patches is actually increasing over time. It's quite still unsatisfactory in the sense that I would have liked this to give me a stable solution. Instead, it's a transient solution. But it's interesting because you have a growth of these patches, and actually you see that the evolution is actually dependent on the curvature of the front. And you can give an interpretation. Actually, Ehud Meron did that in his book on how this is happening based on the front velocity. You can model it also in simpler models, like the Fitzhugh-Nagumo model. And yeah, and basically you can get some understanding of why this is happening. That this is a front control, interface controlled phenomenon. You can also see it by this plot, which is showing you the growth in time of the average patch area as a function of time. It's logarithmic, but you will see that the slope is more or less 1. And so the radius of these guys is going like t to 1/2. And so, well, this is typical for phenomena where this is interface controlled. Anyway, going back a second to this, by switching off then, of course, again, by switching back on a couple of these feedbacks, which before we switched off, like the root infiltration feedback, or by again bringing to being finite the diffusion rate of overland flow, we find that actually the same pattern we had here before goes back to a more regular pattern. So indeed, it is those mechanisms which control limit the size of these, lead us to having a finite size. Okay, let me just accelerate a bit. So, so let me go to this, which is now the real connection to finally going slightly more to the atmosphere. We have seen that we have multiple stable states of pattern vegetation, but these also translate to multiple stable states of soil water. So the next question is, do these transform also to multiple stable states or different alternatives at the same precipitation level in evapotranspirative fluxes? The reply is obviously that as long as I do idealized experiments as I did so far, where I'm in a periodic box and I have precipitation, obviously what is falling in must come out again. And so obviously my evapotranspiration in the end must exactly be the same as the precipitation I got. But we studied this in a slightly more complex model where we introduced a second soil layer. And so basically this is a, this is a slightly more complex model by inclusion of a second soil layer. This because this allows you to be slightly more accurate in the representation of what happens in dry lands, because you will typically have the formation of a very thin, dry upper layer from due to evaporation, which will then obviously limit somehow further evaporation from that surface. But still, you will have the vegetation being able to draw water from the deep soil, so from a deeper soil layer, So that would be this S2 is water in the deeper soil layer. And you can combine this to basically a variation on the theme, which is basically this model as before. So we have infiltration is acting on the upper soil layer, then this water is infiltrating to the deeper soil layer, and then vegetation is actually transpiring from that layer. So that is well, these are details basically. But the interesting point is that obviously, well, the first test is that such a model is still sort of, let's say, a model as before. It's able to reproduce the patterns. It has basically a similar behavior. And then if you take actually, if you take transpiration underneath, basically transpiration just averaged after a precipitation event, what we did here was to force precipitation to now with not assuming a uniform precipitation, but assuming precipitation which is varying in time with a slightly more realistic change for, which is typical for dry lands. And if you do that, let me see if this is the right slide. I guess it's one, yeah. Okay, sorry. So obviously you still get the patterns, you still get the biomass density being reproduced as before, you still have bistability of coexistence of two alternative states. But then if we take now, look at the transpiration per unit biomass, that's the point, or per unit vegetated area, we will discover that actually also these, there is a difference between these two. And notice that this is by unit vegetation. So not taking into account that actually different patterns may have different fractional coverages associated with them. So it has been normalized to that. So basically, so actually, well, but the main point is that actually the geometry of these patterns may play a role. It plays a role. 10, 15% is probably not much, but still it is significant that you can get this. And so how much time do I have? 5 minutes? Okay, good. That's good.
You have 10 minutes now.
10 minutes, yeah, okay, that's good. So one example here is, another conclusion you can get okay, sorry, let me go back. So I think this is already an interesting point. There are other considerations you can make on this. For example, one thing we did was to study what happens if, as humans, we sort of impose a pattern on the system. I mean, we do agriculture, or we do some modification on the landscape by which it's us choosing the pattern. So in this case, you could make different experiments where you take the natural vegetation which would be formed at a certain precipitation level, let's say it's one in the center, and then just rescale this image. I'm zooming the image, making it smaller or making it larger. And obviously by doing that, the fraction of coverage is the same in all these images. No? The percentage of green dots, the percentage of green area is the same, has stayed the same. I just zoomed the image to being larger. And so we have the same biomass density, the same fraction of space covered, etc., etc. And still, if we now force the system to start from such a pattern and to have such a pattern, and then we look at soil water, evaporation, and transpiration, we see that actually this indeed plays quite a significant role. So as a function of the domain size, and the cross tells you what was the original domain size, basically, you see that as a function of the domain size we are sort of imposing, you get different levels of transpiration from individual patches. And this we could probably also understand in the sense that if we take now this, we scaled the pattern, but we did not scale the length of the root system in a sense, because the model stayed the same. We did not touch the model. We just changed the pattern. And if you look at the width, sort of a cartoon of the width of the root system here, you would see that some of these guys are could still be competing for the same resource with each other. So the root systems are overlapping. It's easier to see it for the root system, but it's also true for overland flow. And here instead, they have a larger bare area around them, so a larger reservoir. So it's obvious that they may be able to draw more water. And so transpiration per patch may actually be higher. As I said, there is a trick here, which is the fact that the integral of all this stuff is still conserved. So it's true for the individual patches. And you can also do things like this, which is basically, this is an analysis of the soil water under the patches as a function of this imposed domain size, and starting from different initial domain sizes. So this L0 equal 4 would be the experiment we have done before, basically. And we change the imposed scale to which we scaled the domain size. And you can see that actually, and this is the soil water under vegetation patch. And you see that the minimum of this red curve is reached actually exactly at the level at which we start from. So basically, it is the natural vegetation which forms a pattern which forms which the system forms by itself is that which is able to reduce the soil water under a patch to the minimum level. So basically, it's the most efficient one in reducing soil water. And the same is actually true even if you start from other original domain sizes and again try to vary them. So you see that all these curves, which are labeled with 8 meters, 6 meters, etc., have their minimum exactly at that number. So basically what this is telling us, in a sense, is that these small-scale patterns and all these mechanisms which we have discussed, which were examples of local feedbacks which actually locally to form such patterns, they may also play a role in the controlling the evapotranspirative fluxes to the atmosphere. And now we are going to a slightly larger scale, which is, well, here I have this slide, which is actually citing a paper which some of the people in this room actually wrote, which is a sort of perspective paper, which had this very nice idea that actually we should start really thinking about this, that we have local feedbacks acting at different scales, and some of these scales are actually not at all represented or cannot possibly be represented in modern regional or global climate models. And, but still, you may have cross-scale interactions which actually can lead to these local regional feedbacks, local feedbacks to actually play a significant role and to be important. So it's a plot on the right which is sort of illustrating this idea that you may have a formation of, you have these feedbacks acting locally, and you still may need to find an appropriate parameterization to take into account these phenomena also in a larger scale vegetation model. And these then will be interacting with the other typical feedbacks, which are typically acting at a regional scale or at larger scales, which are well-known feedbacks in the climate system, which are indeed to some extent represented currently in regional and global climate models. And so this connection is I would say, still missing, and it would be interesting to pursue it further. I have a few slides in the end on more recent work, which we have done with an example of a more, say, well, of a local feedback, but which is already acting, or which is visible also when you simulate vegetation in a more global type of model. And it's about African savannas. African savannas, or more in general, tropical grassy biomes, so grasslands and savannas, they can be opposed to the tropical forests. So you have these two types of systems. On one hand, you have a system which is characterized by grass, a combination of grass and trees, basically. And the point is that both the grass and the trees are shade intolerant. They do not like to have a closed canopy above them. And they're both basically, well, in a sense, even the grass, sorry, this is dumped. And the trees actually in these areas are actually fire tolerant. So they will survive fire events. And the grass itself is obviously creating fuel to promote the occurrence of fires. So there is a feedback at work there by which the accumulation of grass, the growth of grass, will possibly facilitate the occurrence of fires, but this will help to keep an open canopy, and this will help also the trees, which are actually fire resistant, to survive in these areas. And we can oppose this to what happens in tropical forests, where instead the trees are actually shade tolerant, but they are they will not resist happily easily to a fire. And they obviously, by closing the canopy, they're also reducing the amount of grass. And in this way, they are preventing, in a sense, the likelihood of such fires to occur. And so we did a study on this. Actually, this was based on observational data. This is a series of MODIS data, actually, for various areas. There was quite some extreme filtering to avoid areas, to basically keep mostly natural areas, so to avoid areas which were too heavily affected by anthropogenic influences. And basically, some of it is summarized in this type of plot. And what you can see here is, for example, on the left is mean annual rainfall and the percentage of tree covers. And we can see that, for example, there's a wide range where actually you can have, at the same precipitation level, you can have the coexistence, or you have both possibilities, both solutions. You can have both savanna-like vegetation, which would be the red and blue points, and you can have tropical forest type of vegetation, which is forest. So associated with different levels of percentages of tree cover, but at the same level of the control parameter, which in this case we could consider to be the precipitation. And the fact that this is related to fires, you can actually see it when we color, in this case, the percentage of grass cover here with the average fire intervals. So a yellow would be a frequent fires, and blue, the darker, the more blue color or violet color is actually extremely rare, if not unlikely, fires. And you can see that actually the two alternative states are also characterized by different fire regimes. There's also other factors, of course, at play. So one of them is also seasonality of precipitation. And actually, this was studied in a separate paper. You see the citation basically down there. So if we go back to the role of fires, for example, here you see it also summarized. Well, sorry, this is a distribution of how these distribute. And you see that actually there are some areas where both states can coexist. And then you find sorry, where is it? Yeah, here you can see, well, you can do such an analysis that actually, yeah, they are actually indeed characterized by very different fire regimes. And also there is a strict relationship, of course, between grass cover and the average fire interval, which is a further evidence that such a feedback may be at work. On the intraseasonal rainfall variability, the result of that paper was that actually, that's also an interesting one, but it's more complex, and if you want a little bit less evidence, but the point is that you see an impact of the intraseasonal rainfall variability. Some variables really depend on this, but actually the effect is a function of the average annual precipitation. So there is a difference between very dry areas and very humid areas. Anyway, in any case, you can still derive some conclusions on this, and possibly also make some predictions what you could possibly expect in a future climate. And then last point I want to show is actually an analysis which can be done if you actually do the same. Instead of doing it on data, you do it on model data. So this is an analysis on data from the dynamic vegetation component, which we find in some global climate models. In this case, we use two. One is actually from Hamburg, and the other one, so JS Bach, and the other one is LPJ gas, which is the one we're using in the ECJ model. And this type of analysis can now be used, and is useful actually to sort of check if the models are able to reproduce this mechanism, because you would expect them, ideally, to give you exactly the same pictures as this analysis we have done before, based on purely satellite data. And to some extent, you do get that, and you do get that. There's obviously some obviously, if you look carefully at these images, you will find some things which do not agree well with observations. So you compare the right column with the left column, which is the reference. So you obviously find some differences, and this actually is telling you something about how these models are actually reproducing some of these processes. So for example, here for LPJ gas, the conclusion is that the fire process should be improved, because you see that, for example, this middle picture where we color this with the fire frequency, you see that that is very different in the LPJ gas model compared to the observations. I must say that this is a previous version of LPJ gas. There is a new one which is under development, but we also gave a look at that, but well, there were other issues there. So no, this is not the place to discuss those. And the same could be done for JS Bach, and here you see, actually, I would say for the fire is a much better picture. And, but also in this case, obviously, you can sort of draw some conclusions. For example, well, here, there's just a list of some of them. And this also leads you to some suggestions of what possible maybe be looked more and better in these models, and what possible, which processes could be improved. But the main point, as I said, is really that you do indeed have this this bimodality which is reproduced in JS Bach. Yeah, and that's it, I would say, and with this I would conclude. And so even if the title was going from the patterns to the more global, regional and global case, this is totally still open, and I'm sorry I could not provide a complete solution to that. But still, I think this is really an interesting and active line of research which should be further pursued. Thank you.
Yeah, thank you very much, Jost, for bringing us to the world of patterns and also to advance the models, biospheric models. Questions? Martin?
Yeah, briefly on time scales.
You don't have a mic.
Okay. Okay. How long would it take if you perturb the precipitation for the vegetation pattern to change from one pattern to the other? Have you done also field experiments on this, not only numerical?
Okay,
so just doing some watering of the plants, or just take out the water, and how long would? Is it months, years?
So it depends on the species. So for if you reproduce these shrubs, this tiger bush, that is a very slow process which takes decades. But that is also a process which, if you compare aerial photographs, is probably taking decades or hundreds of years in real time. So that is also in reality. For grass, it's obviously a much faster process, and it is also such in the model. I mean, we have obviously non-dimensional time, we have heavy approximations, but you can translate these. And yes, there have been some experiments which a group in Israel did. They tried to do some of these experiments. So trying to do under controlled circumstances in a lab to grow some of these patterns and actually observe them. So it is feasible also in real time, yeah. And actually, the first picture I showed, that lawn, that labyrinthine pattern, which was actually on a lawn in a residential area, that appeared over a few days of non-irrigation. That is actually a very fast one. This said, the problem of timescales, obviously, we have strong limitations in these models. We still need to have quite separate timescales between the different dynamical variables. So since it's based on a Turing-like mechanism, they cannot get too close. So, but I must say the values are not unreasonable.
More questions to Jost?
Maybe you can hear me. Thank you. I think it's fine.
Yeah, I can.
Yeah. Thank you for your talk. I think it's related to timescales again, but maybe more technical. Like where you saw the example, the intermittency in rainfall. My experience with these models is that precipitation grows quite slowly, and once the patterns are formed, even if you are perturbing them with rainfall, they don't change, they don't respond so much.
They cannot, no, they don't.
Can you enlighten us a little bit on this, like in your
No,
simulations, for instance, or more generally,
how
could we get this effect of changes in rainfall to be shown?
So in fact, I did not say that, but in most of the slides I showed you, we assumed that precipitation was basically not varying at all. We kept it constant. So there was that work where we actually varied precipitation. Then there's another one where we also studied the effect of rainfall intermittency on such type of a model. But always, I must say, so in the example you saw, the pattern was not varying at all, indeed. So even if the rainfall is varying quickly, what is changing is water in the soil and the evapotranspirative fluxes. Those are fluctuating, but indeed the parameters are such that the growth of the vegetation and its lateral diffusion, they are all very slow compared to the other timescales in the problem. So indeed, the vegetation will react only slowly to that. Still, it's interesting because you can actually have some cases where you can show that having an intermittent precipitation, depending on the form you choose for the transpiration part, you can have a nonlinear effect by which actually this may help somehow to extend the range of existence of the vegetation. So having intermittent precipitation may help the vegetation actually to live in a wider range of average precipitation compared to a more constant type of precipitation. And yeah, so this.
This is more of a comment. You did start with that striking satellite picture of the border between the Egyptian Sinai and the Israeli Negev. What you didn't mention is that actually that was something that was observed from the first geoscientific satellites by Joe Otterman, and it suggested to Charney the famous biogeophysical feedback that Martin talked about in his lectures last week. So, you know, it's interesting in any case that it's persistent over decades and has played quite a role in the field.
Yeah, just also a question from my side on the fire model. Do you think that our fire models will be improved because the main trouble is to get grass competing with trees, and usually we are not doing that well inside the dynamic vegetation models?
So obviously it's limited to the savanna area. So and the point is that of course in such models you're sort of striking a compromise for fires all over the world. But indeed, yes, I agree that is a point where there is hope to have some improvement. Indeed, yeah.
Yeah, please.
In some of the more ambitious scenarios of the integrated assessment models, they reforest a lot, particularly in Africa. I'm wondering if anyone's looked at, you know, how that would work in terms of the changing moisture patterns that come out of the climate models, because I'm pretty sure they're not in the integrated assessment models.
I know that that is an open question at the moment, and I recently read, I now cannot recall, but I read that this is a question which, it's not the first time I hear this question, so I think that is being investigated now, but I'm not aware specifically now of any specific study. But yeah. But indeed, that is true. There is this type of heavy interventions would completely change the balance between savannas and forests in such regions, and with not completely obvious consequences. Yeah.
Any other questions?
So now I need to go home and do the simulation. So we can
if not, then thank you again.
Thank you.